Since the two Voyager probes have been traveling across the vast reaches of space for 47 years, providing us with ever-new insights into uncharted cosmic planets as humanity's most remote outposts, there is a name for the greatest success story in space travel, and it is not James Webb, no. However, how can the odd differences that the probes have recorded at the edge of our home system be explained? And what about the enormous, enigmatic, wrinkled structures that lurk in the heliosphere looking back? The identical sister probes have now even ventured into interstellar space, revealing to us that the regions at the solar system's edge are far stranger than previously believed. The year 1977 seems to be from another planet, as it was the year Jimmy Carter was elected President of the United States, the last time the guillotine was used for an execution in France, and the cult movie Rocky won 3 Oscars. However, as everyone knows, there was another event that occurred in 1977 that continues to this day: the launch of the 2 NASA space probes, Voyager 1 and 2. Voyager 2 was the first to bid farewell to Earth. Voyager 1 set out on August 20th, 1977, to explore the previously largely unexplored areas of our outer planetary system, followed 16 days later on a different trajectory, but no one could have predicted at the time that this was the beginning of what would ultimately be the longest-running mission in modern space travel. Between them and the Sun, because, as was previously mentioned, the probes had only set out to gather new information about the outer planets of the solar system, and the endeavor was not even under a lucky star at first. Fortunately, communication issues with Voyager 2 were resolved quickly by NASA experts, clearing the path for the historic mission that set out for unknown worlds. Today we live in a time in which the James Webb Telescope presents the outer representatives of our planetary system to us in an unprecedented level of detail. But almost 50 years ago, the situation was completely different. When Voyager 1 and 2 set out into space, our knowledge of the distant planetary worlds was, to say the least, limited. And so it came to pass that the first items on the research checklist list concerned the Jupiter and Saturn systems, and that the terrestrial experts were soon enriched with many extensive measurements and numerous images in the process. Our understanding of the gigantic gas giant and the iconic ringed planet was taken to a whole new level, and while it was then time for Voyager 1 to set a course for interstellar space, the further journey of Voyager 2 had a few more exciting stopovers in store. A corrective maneuver in the spring of 1981, and later the probe was on its way to Uranus, which it reached on January 24, 1986. And just to be clear, by this point, Voyager 2 had already exceeded its originally predicted lifespan by a factor of 2. However, since the spacecraft apparently didn't care much about any earthly predictions, it not only took a close look at Uranus, but also discovered 10 previously unknown moons of the remote ice giant. In the same breath, the next stop was to be Neptune again, and this time it was supposed to be the final chapter of the research mission. There were simply no plans to fly by any other destinations, which is why the more than 9,000 photos taken by Voyager 2 of the outermost planet in the solar system were at the time tantamount to a pictorial farewell. However, the probe did not just diligently take pictures of its surroundings, but also added 9 previously unknown satellites to the star map's Triton. The largest of Neptune's moons, and already known at that time, was to be examined in detail in the course of this Voyager 2, provided the insight that its diameter is not 5,000 kilometers, as previously assumed, but only 2,760 kilometers. Furthermore, it found that the brownish-white surface of the satellite had surprisingly few impact sites, and that numerous geysers are dormant here, regularly spitting liquid nitrogen onto their surroundings. We must go back a little to 2012 in order to attain the next milestone of the Voyager program. This is not surprising, because the far-off region that the Sun's powerful arm can no longer reach is not exactly around the corner. The interstellar medium that fills this far-off cosmic region is primarily composed of dust and ionized. Although atomic and molecular gas make up the interstellar matter, electromagnetic radiation and the galactic magnetic field complete the interstellar medium. The spacecraft are taking unprecedented measurements here, just as they did on our planet's doorstep when Voyager 1 and its sister probe passed the solar system's boundary in 2012. However, because the probes are not traveling in the same area, Experts have had the exciting opportunity to study the interstellar medium at two different locations and compare them. Consequently, an important task of Voyager 2 is to check the data collected by its twin probe for similarities and differences, and indeed a lot of information from Voyager 1 should be confirmed in this way. For example, the density of particles. In interstellar space, however, things get even more interesting, not to mention confusing, when we look at the ways in which the probe's measurements differ dramatically, what Voyager 1 and 2 have discovered at the edge of the solar system to understand the Voyager discoveries properly. However, we first need to understand how the boundaries of the solar system are structured. Basically, there is a dynamic network of magnetic field lines around the Sun that is invisible to the naked eye. These in turn act as paths along which electrically charged particles are shot into space, the so-called solar wind. And while the solar wind spreads throughout the solar system, it eventually reaches the interstellar medium. But just like oil and water, the solar wind and the interstellar medium do not mix perfectly. As a result, the solar wind forms a bubble in the interstellar medium called the heliosphere. And thanks to the Voyager data, we know that it extends about 18 billion km from the Sun into space, and in the outermost edge of this region, the heliopause interstellar space finally begins. And before Voyager 1 entered the threshold of the solar system, practically nothing was known about this area. However, the findings that the probe sent to Earth in this regard immediately left researchers in a state of both amazement and confusion, because many of their predictions had simply been wrong. For example, the interstellar magnetic field is in fact almost 3 times stronger than previously assumed, which means nothing less than that the interstellar particles also exert about 10 times more pressure on the heliosphere than written in the theoretical models. But as groundbreaking and novel as the Voyager 1 data may have been, they were also accompanied by a major drawback. They were incomplete. This was for the simple reason that the instrument for measuring plasma temperature has been defective since the 1980s. However, since the counterpart on board, Voyager 2 was still working. The researchers were all the more excited to see what information the probe would collect as it approached the heliopause, and today we know that the plasma around the probe increased its density, while at the same time, it slowed down and heated up beyond the heliopause. The interstellar medium reaches temperatures of almost 30,000 dC, which is significantly hotter than the scientists had predicted. However, since the plasma has an extremely diffuse and thin inconsistency, the temperatures around the space probes are surprisingly low. Furthermore, Voyager 2 found that the plasma crosses over from interstellar space into the heliopause and in the opposite direction. When Voyager 1 crossed the heliopause, it encountered compact extensions of interstellar particles there, but strangely its sister probe was confronted with a kind of particle stream that extends more than 150 million kilometers into the heliopause. No less strange is the fact that Voyager 1, about 1.3 billion kilometers before the heliopause, entered an area in which the solar wind slowed down noticeably. All in all, however, these strange differences reflect only a fraction of the mysteries that still need to be solved in the future regarding the edge regions of the solar system. For example, we don't even know exactly what shape the heliopause has, but at least we now know that the heliopause is surprisingly wrinkled, the enigmatic structure of the heliopause, because after the researchers at Princeton University had registered an immense increase in solar wind pressure of almost 50% within a few months, they used the data to reconstruct the shape of the heliosphere and the heliopause, with the astounding result that the heliopause has gigantic folds that extend tens of astronomical units into space. Just to recap, the length of the astronomical unit corresponds to the mean distance between the Sun and the Earth, which is around 150 million kilometers. So we are talking about folds that are several billion kilometers in size. No amount of Botox will help here. But perhaps the information that the experts have been able to gather about the background to the wrinkle structures will help us. These are the specific outcomes of the high-energy particles colliding with the solar plasma after returning from the heliopause in waves. As a result, we learn that the heliosphere is not a static, unchanging entity, but rather a dynamic one that constantly billows, dips, and unfolds again. In fact, the cosmic folds are chasing after the Voyager probes because, even though they are very old, They continue to expand as soon as the solar plasma smooths the fold structures again. Voyagers 1 and 2 will be spared the folds in their necks because they are simply flying too fast to be caught by them and will be returned to the inflating heliosphere. However, the chase of the folds means that the probe's distance from the heliosphere is not increasing as quickly as one might initially think, and we would be thrilled if the distance between your finger and the subscribe button now decreases much faster than you would initially expect. Please give us a thumbs up and subscribe so that you don't miss any more of our videos. We hope to see you soon.